Welcome to my series of videos on writing and writing of names and formula writing for a variety of compounds. And actually what I'd like to do is in the next series of videos I would like to focus on, first of all, ionic naming and formula writing, and with that I'd like to include hydrates, which I'll explain as we go. I would also like to do binary covalent compounds, and I would also like to do acids and show you how you write names and also how you write formulas for these various sorts of compounds. Now, as far as ionic, I'm going to actually break that up a little bit, and I'd like to start by talking a little bit about the names of ions and, of course, what ions are. An ion is an atom or group of atoms that has either gained or lost electrons and therefore has a charge. If you think about an atom by definition is neutral, which means it has as many protons in its nucleus as it has electrons going around the outside. Well, as long as those two numbers match, of course it's neutral. Well, if I take and remove some electrons, it's going to become positive because now it will have more protons in the nucleus than electrons going around the outside. Well, ions that do this are known as cations. Cations basically are going to lose some electrons, and as they lose electrons they become positive. Now, where are these as far as monatomic cations? These are typically things like your alkali metals in column 1 and your alkaline earth metals in column 2. The reason they do this is because these elements generally have a full shell, and in the case of the alkali metals, 1 extra electron. In the case of the alkaline earth metals, 2 extra electrons. So as they join with other atoms, it's fairly easy for them to lose that 1 or 2 electrons, and in the process take on a +1 or +2 charge. Now, the elements in the middle, the transition metals here, they also take on these charges, and they, for good or bad, many of them can take on several different charges. And so what will happen is something like iron, cobalt, and nickel can be either +2 or +3. Cobalt can be +1 or +2. They don't all do this. Some of them, like zinc, is always +2. But there's a variety of ways we're going to treat that. We're going to actually use Roman numerals, which I'll get to in just a moment. What I want to do before I do that, though, is mention the other side of the table, and those are your anions. These are the guys that tend to gain an electron or several electrons and therefore become negative. And if you think about it, that makes some sense. When you look at the halogens here, they have a full shell and 7 outer electrons. In an effort to fill the second, third, or fourth energy level, the outer portion of that level, the S&P shells, they tend to need 1 or 2 electrons more if they're the oxygen family, the chalcogens. So what ends up happening is those guys tend to take on, the halogens take on a -1 charge. The chalcogens, or the oxygen family, tend to take on a -2 charge. So this whole process of gaining and losing electrons is an effort to become stable, and it's an effort to get a full outer shell. Now, let me go back and talk about the naming of these things, and let's start with the cations first. The cation name of an ion generally doesn't change. So for instance, if we're going to do something like, say, salt, which many of you know is NaCl, when you write the name of the Na, you just write sodium. You don't really change anything, and so this would be sodium. But in the case of the anion, if it's a monatomic anion, meaning it's made of one type of atom, we change the ending to IDE. So many of you know this is not sodium chlorine, but we call it sodium chloride. So notice I've taken that chlorine ending and changed it to chloride. So typically with monatomic anions, that's what you do. So this would be the simplest case, where I have one atom that is my cation and one atom that is my anion. Now, what do I do when I have one of these guys that has several different charges? Well, I need to let you know, if I'm writing the name, if I have, say, iron 1 or iron 2. So what I do is there are 2 different ones. There's one iron that will lose 2 electrons and become +2. There's another iron that will lose 3 electrons and become +3. So when I write the name, what I do is, as I mentioned a moment ago, I use Roman numerals. So this would be iron 2, this would be iron 3. And so oftentimes you'll see names written where it says iron 2 chloride or iron 3 chloride. I'll go over how to write those formulas in the next video, but in general what you need to know is that Roman numeral in the name is telling you the charge of the cation, the first thing. Now, we also have a class of anions that is made of more than one atom. If you notice a moment ago, I called this a monatomic because it's made of one type of atom. You can also have polyatomic. Polyatomic anions are made of more than one atom. In this case, what I want to show you is there are some rules for things that are called oxyanions. Oxyanions are typically made of a nonmetal combined with some oxygen. What happens here, if you look, you'll see that we have the chlorate ion. The chlorate ion is the ClO3 with a -1 charge. What we do here is the most common oxyanion gets the ending of ATE. This would be the chlorate. Now, if I can take one oxygen away, but it still keeps the same charge, I call that the chlorite. If I can take away another oxygen and still keep the same charge, I now add the prefix hypo. So this would be hypochlorite. Now I can also go the opposite direction. If I have a ClO3 and I can add an oxygen and keep the same charge, then I add the prefix per. So this becomes the perchlorate. So ClO3 is the chlorate, ClO4 becomes the perchlorate. Now the nice thing is a couple of things you should know. The most common oxyanion out there generally gets that 8 ending. So for instance, just to pick another example, SO4 with a -2 charge is called a sulfate ion. If I had SO3 with a -2 charge, that is your sulfite ion. So the nice thing with the the polyatomic oxyanions is really all you need to know is the 8, or really any of them, and you can figure out by adding or subtracting oxygens the names of all the others. Now a lot of times you can find these in lists. I know with my own students I usually give them a reference packet which at least has most of these 8s in there. If they ever need the 8, they just take one oxygen away from the 8, so it makes it rather easy. So I hope this has helped you. In my next video I want to start putting these together into formulas and names and show you how all this works.